Inside the central bookstack of Yale's Beinecke Library sits MS 408, universally known as the Voynich Manuscript. For over a century, this text has been surrounded by theories of magical origins, extraterrestrial contact, and supernatural intervention. We are going to put those aside. MS 408 presents a highly constrained, unsolved dataset, a physical and statistical challenge to modern researchers. To understand this artifact, we must isolate the text within two unforgiving parameters: the chemical boundaries of 15th century codicology and the mathematical laws of information theory. Any valid decipherment theory must survive the physical reality of the ink and the computational architecture of the text. This creates an inescapable analytical box. Radiocarbon dating places the creation of the vellum precisely between 1404 and 1438. The physical construction is highly irregular, featuring a non-standard bifolia sequencing and inexplicably complex folding architectures. Typical 15th century illuminated manuscripts follow a rigid format of neatly nested quires. MS 408 ignores these standard medieval bookbinding conventions. We can narrow the physical window further by looking at the ink. In 2009, the McCrone report conducted an X-ray diffraction, or XRD, analysis on the manuscript's pigments. This readout isolates the specific chemical compounds detected in the red-brown paint. The crystal phases characterize hematite, iron sulfide, red ochre, and palmierite, all materials consistent with medieval European production. Equally critical is what the XRD analysis did not find. There are zero traces of modern synthetic elements, specifically post-1916 titanium white with an anatase structure. The chemistry definitively rules out a modern forgery. The antiquarian Wilfrid Voynich could not have created this artifact. It is irrefutably a product of the early Renaissance. Shifting from physical chemistry to statistical breakdown, we look to the work of cryptanalyst Prescott Currier. Currier discovered that the manuscript contains distinct generative systems, which he labeled Language A and Language B. These distinct languages correlate strictly with two entirely different handwriting styles across the bifolia. Because MS 408 is not a monolith, decoding attempts treating the entire book as a single cipher are likely to overlook underlying structural data. To understand why decryption efforts fail, we apply Shandon entropy, which measures the amount of unpredictability within a dataset. A critical cryptographic rule states that simple substitution ciphers do not alter the underlying entropy of the original text. This log-log plot visualizes Ziff's law, graphing word rank against frequency. These downward slopes represent the standard distribution for natural human languages. When we plot data points from MS 408, they align perfectly with this slope. On a macro level, Voynichese mimics natural language. However, this diagram reveals a severe contradiction. While individual characters show normal variation, the text features severely restricted character transitions and abnormally low conditional entropy. This means knowing one character makes the subsequent character highly predictable. This degree of rigid predictability contradicts the standard orthography of known European languages, like Latin or German. The text exhibits a final statistical anomaly, a strict binomial distribution regarding the length of its words. Voynichese lacks the long, multisyllabic words that occur naturally in known historical records. The text is a statistical paradox. It is too structured to be random noise, yet too predictable to be a natural human language. This paradox explains why recent claims of artificial intelligence deciphering the manuscript have not produced a verifiable translation. Natural language processing models rely on hidden Markov models to predict transition probabilities between characters. These models require an underlying vocabulary with verifiable semantic mapping. Without ground truth data, the transitions break down and output empty variables. Artificial intelligence fails here because a language cannot be algorithmically translated if the generative architecture itself is synthetic or unmapped. If the text is not an encoded language, we must consider how a 15th century author could create these precise statistical anomalies. One possibility is the Cardan Grille, a physical algorithmic tool available in the 15th century. A scribe moves a physical grid over a table of text prefixes, midfixes, and suffixes to synthetically generate text. This specific mechanical action, reusing the same character combinations through cutouts, natively produces low conditional entropy. The physical constraints of the grid naturally enforce the binomial word length distribution found in the manuscript. This hypothesis suggests MS-408 functions as an empty statistical shell, engineered to mimic the visual structure of meaning. These physical constraints are rigid. The artifact is an undeniable product of early 15th century European chemistry. The statistical data forces a choice between a highly restrictive, historically anomalous cipher or a dedicated algorithmic hoax. Single-discipline approaches, whether purely computer science or purely material history, continually fail to account for the full dataset. Brute force computational analysis will not output a translation until the mechanics behind courier languages A and B are fully mapped. The ultimate solution to the world's most mysterious book lies only at the precise intersection of quantitative pattern recognition and material science.